All right, so composing functions or function composition starts with just the general idea of if f of x equals 6x minus 7, find f of 3. What's that mean do? We'll put 3 where x is, so 6 times 3 minus 7, which would be 11. So f of 3 is equal to 11. That's what function value is. Function composition is instead of plugging in a number, we're going to plug in another function in the place of x. So function composition f composed with g of x means take the function g of x, put it in the place of x in the f of x function. Okay. The domain of a composite function, it's the set of all numbers, in our case x, in the domain of g of x, second function, such that g of x is in the domain of f of x, first function. So it may not always be g of x and f of x. Sometimes they may turn that around. Okay, so what's that mean? That means you're taking the domain of g of x. It has bearing on the problem, but then the y values, the range from g of x, becomes the x values or the domain for f of x. The second function's range becomes the domain for the first function. And we've got to deal with some issues that might occur based on that. If there are no restrictions on either of those functions, then we don't have any restrictions on the composite function. But if there are restrictions on the second function or the first function, then we're going to have some restrictions on the composite function. It makes sense there that there's restrictions on the pieces, then there's got to be a restriction on the whole thing out of that. So let's look at example B. F of x is equal to 2x squared minus 3. G of x is equal to 4x. Two pretty tame functions. Let's first find the domain of each of them. Well, f of x is a quadratic function. Are there any restrictions on the domain for a quadratic? No, it's negative infinity to positive infinity for all real numbers. G of x is a linear function. Are there any red flags or restrictions on the domain of a linear function? No. So it's all real numbers as well. Negative infinity to positive infinity. So without even finding the composite function, because we know there are no restrictions on the pieces, if I wanted to find the domain of f composed with g of x, then the domain, since there are no restrictions on the pieces, there are no restrictions on that domain. And then we want to find f composed with g of x. That's our last job for this problem. So we're taking the g of x function and replacing x in the f of x function. That's what our job is, to find f composed with g. Remember, f composed with g means take g of x and replace x in f of x. It'll be 2 parentheses 4x squared minus 3. And we just simplify that as much as possible. 4x times 4x would be 16x squared times 2 is 32x squared, and then minus 3. So f composed with g of x is 32x squared minus 3. And again, you can look at that composite function and see there's no red flags in it either. So it makes sense that it has that domain of all real numbers as well. Okay. So nice when there are no restrictions out of that. A function value works the same way in composite functions as with regular functions. Take the composite function, plug in the x value they want you to find. And it's nothing different than that. Okay. All right. Here's f of x, 1 over x plus 5. Here's g of x, 4 over x minus 1. Okay. Our job is to find f composed with g of x and its domain. Okay, that's our job. So I'm going to find the domain before I find the actual composite function. Okay, to do that, I need to find the domain for each piece first. What's the restriction on f of x? X cannot be negative 5. Because we have an x in the denominator, that's a red flag. We set x plus 5 equal to 0. We get x can't be negative 5. Okay. What's the restriction on g of x? X can't be positive 1. Same kind of red flag. Got an x in the denominator. We set the denominator equal to 0 and get x can't be 1. Okay, so now here's where it gets a little bit muddier. Is when you're doing a domain of a composite function, the y values of the g of x function, the second function, are actually the domain of the first function. So what we've got to do is we've got to answer the question, when does g of x meet this restriction? When is the y value for this negative 5? Okay, so what we have to do is set that part of the when does g of x equal negative 5? When does the second function equal the restriction from the first function? Okay, so we set 4 over x minus 1 equal to negative 5. And solve it. So cross multiply, 4 equals negative 5x plus 5, just by doing the distributive property with negative 5 and x minus 1. And then subtract 5, 1 equals negative 5x divided by negative 5. 1/5. X can't be 1/5. Okay, so there's a restriction on the composite function. So the domain on the composite function, f composed with g of x, it's all x's such that x cannot equal 1/5 and 1. What are those parts? Well, the 1/5 came from setting the second function equal to the restriction on the first. That's the 1/5. The 1 came from the domain of what? The second function, g of x. Okay, so you find the domain of the composite function, and there are restrictions on both of them. The restriction from the second function will be in your domain, and then when you set that second function equal to the restriction of the first function, that will be in your domain. Okay? If the first function has no restrictions, then you don't have to do that step. It makes sense that if it's got restrictions, you got to do this. If it doesn't, you don't have to do that.
Is the second function's restriction always going to be in the...
Absolutely, yes. Okay. The second function's restriction will always be in your domain of your composite function. Always. Great observation. Yes, sir.
So when you were turning 4 over x minus 1 equals -5 and 4 is equal to -5x plus 5, you just multiply the denominator by both sides, right?
Yes, that's exactly what I did. Yeah. That step that I'm doing there is multiplying x minus 1 to both sides. And then doing distributive property. How about that? Okay. So there's our domain of that composite function. Yes, that's what I'm doing. That's what that shows there. Okay. Now we need to find the composite function itself. So we're taking g of x and replacing x in f of x. So f composed with g. So that'd be 1 over, instead of x, we're going to put 4 over x minus 1, and then plus 5. It would be wonderful if we could leave it that way. But a fraction inside of a fraction is a no-go. Okay? Can't have that. So we've got to do a little bit of work here to simplify this. So anytime that I'm going to add a fraction and then a regular number, what do they both have to have? Common denominator. Right now, the 5 has what as a denominator? 1. So it's over 1, right? What would be the least common denominator between 4 over x minus 1 and 5 over 1? It'd be x minus 1. So the second fraction needs x minus 1. But if the bottom part gets it, so does the top. So most of these are not going to be just overly complicated on what your common denominator is. It's usually that, or that is. Multiply the bottom and top by that. On the top, we get 5x and minus 5. So we have 1 over 4 plus 5x minus 5. Now they've got the same denominator, so I'm writing it as 1 fraction over x minus 1. I can simplify that part right there because 4 plus 5x minus 5, we got like terms. You got the 4 and the minus 5 on the end. Yeah, it turns into 5x minus 1. 1 over 5x minus 1 over x minus 1. Now, I'm darkening in that fraction bar so we see that that's the major fraction bar. Dividing by a fraction is the same thing as doing what? Multiplying by the reciprocal. So this is 1 times x, so x minus 1 over 5x minus 1. So I've just taken this division problem, this fraction, and rewritten it as a multiplication problem. That's all I did right there. 1, that's the 1. Dividing by this fraction is the same as multiplying by this reciprocal. That's going to be a common thing that you're going to have to do. So keep that in mind. Now, 1 times all that doesn't change it any. So we get f composed with g of x equals x minus 1 over 5x minus 1. Now, this composite function, you could get part of your domain from it. If we set the denominator equal to 0, we get the 1/5 out of that. But we would lose the fact that x can't be 1. So don't just go to your composite function to get the full domain. You've got to remember that the domain of the second function is also part of that. And so don't forget that the domain of the second function is always going to be there. Yes, sir.
So restrictions in the second function, g of x, always just carry over?
Yes. Always. Always just carry over. All right. Let's do another. What letter we're on here? D? Yeah. Kind of skipped around on some examples I've got here. F of x is the square root of x plus 3. G of x is the nice, simple, linear equation 2x plus 5. Okay. Again, let's find f composed with g of x and the domain. We're finding both of those. The composite function and the domain of that composite function. So, what should we do first? All right, good job. F of x. What's the domain of f of x? How do we find that? Okay, so we're getting that from setting whatever's underneath the square root, take that and set it greater than or equal to 0, and then solve that. And that's where we're getting x is greater than or equal to -3. For g of x, are there any restrictions on g of x? No, it's all reals. Okay. Now, even though there aren't any restrictions on g of x, is that affected by the restrictions on f of x? Yes, very much so. How do we find when g of x has that problem? Good. Not 3, but -3. When is g of x greater than or equal to -3? When does it fit that? Because it has to fit that to do the composite function. So we solve that. Subtract 5. 2x is greater than or equal to -8. X is greater than or equal to -4. Now, with that, the domain of the composite function. So the domain, yes, absolutely. That's what it is. Divide by 2 there. The domain of the composite function is what? And we'll do set notation. All right. And then that's it. Why is the -3 not involved?
We had to figure out when the g of x would be at.
Right. And which function's domain affects the composite domain? Second one. And the second one didn't have any restrictions. So the only restriction that comes up is the one that was a result of the first function's restrictions. It gets kind of twisty when it does this kind of stuff. All right. Sir.
So if you were going to find the composition of g of f, like g of x of f of x,
G composed with F, like the other way around. Yeah.
Would -3 be in the?
Yes, absolutely. You stole my next example. Thanks. Way to go. All right. Let's go ahead and find F composed with G. All right. So let's find that actual composite function. So we're taking G of X, the nice linear piece, 2x plus 5, and we're replacing X in F of X. 2x plus 5, and then the plus 3, and then simplify, and yes, you get 2x plus 8. Right here. Compose of G. And there's our composite function. Very nice, easy thing to do there. All right, sir.
I don't entirely understand how you turned the square root of x plus 3 is equal to 0 into x is greater than or equal to 3.
Right here, I took the whatever's inside of the square root. You set it greater than or equal to 0, because what kind of numbers can we take the square root of? We can take the square root of 0, so there's the equal to part. And then only positive numbers get us real solutions. Anytime it's a negative, then it's a complex number or imaginary number. So we set greater than or equal to 0 to define the domain of that to be real numbers, because we want domain is only real numbers. All right. So then I set whatever's inside of the square root is the only thing that gets set greater than or equal to 0. If there was something out here, it doesn't even matter. Okay, it's only what's on the inside. So I'm setting x plus 3 greater than or equal to 0, and then subtracting 3 to get x by itself. And that's where I'm getting x is greater than or equal to -3. Is that the part you were asking about? Okay. Yeah. Anytime it's a square root, you're going to do that.
Yes.
Okay. All right, so let's take. Let's take the other direction. Let's find if f of x is the same function and g of x is the same function. Let's find g composed with f of x and the domain. Okay. Well, we already know the domain of f of x and g of x, right? F of x is greater than or equal to -3. G of x, all real numbers. Okay. Now, in this one, the composition statement is g composed with f. So f is the second function. Are there any restrictions on the first function? No. So do we have to do that work where we're setting the second function equal to the restrictions of the first function? No. There's nothing to set it equal to because it's all real numbers. So there's no restriction to that at all. So we're going to just take that and say, okay, well, the only restriction that exists is on the second function. So the only restriction on the composite function is that x is greater than or equal to -3. That's the only thing we have to have. So domain of g composed with f of x, all x is such that x is greater than or equal to -3. I'm sticking with set notation here as your quiz and stuff.
So the domain isn't greater than or equal to -3, right?
The domain is greater than or equal to -3. There's a difference in the inequality style and when you have an x in the denominator. An x in the denominator, you're looking for when does it equal 0. For this, you're looking for when does it stay positive or 0. So it stays the same there. All right, so there's our domain. Let's get the composite function, g composed with f. So we're taking f of x and replacing x. X plus 3. And then there's plus 5 on the outside. Can we combine this 3 and this 5? No. This 3 is on the inside of the square root. The 5 is not. You can't put them together. There's nothing else you can do that. Just leave it alone. Okay. Let's do one. This section. I'll scroll back up and you see. H of x. X squared minus 5x plus 7. K of x. 3x for x minus 2. Yeah. Find H composed with K. X. And the domain. All right, so find the domain. What's the domain of H of x? Why? Yeah, quadratics don't have restrictions. There's no red flags. Remember, the red flags are x's in the denominator or square roots. Quadratics don't have those. What about k of x? X can't be 2 on the second one. By setting the denominator equal to 0, we know x can't be 2. Which restriction, or does that restriction affect the composite function? Why? That's the key. Because it's the second one, it has that restriction carries over to the composite function. Since there are no restrictions on the first function, we don't have to do any more work to find the domain of the composite function. So the domain of h composed with k of x, it's all x's, such that x is not equal to 2. That's a fun one. Now, the really fun part is the composition here. So h composed with k of x. All right, so we're replacing x in the h of x function with that fraction. So 3x over x minus 2 squared minus 5. I'm going to put that as 5 over 1 times 3x over x minus 2 plus 7. I'm going to make it 7 over 1. Because I know I got fractions, and I'm going to just go ahead and make everything look like a fraction, because it'll help me. When I square 3x over x minus 2, what do I get? Besides a headache. What's 3x times 3x? 9x squared. Here's a shortcut. Instead of multiplying out x minus 2 times x minus 2, just write it as x minus 2 squared. Because it's really not going to help us any to multiply that out. It's actually going to make it harder on us if we do. Okay. Now, the next thing is we're multiplying negative 5 over 1 times this fraction. What does this part turn into? Negative 15x over 1x minus 2. And then 7 over 1 is still 7 over 1. Now, be wonderful if you leave it that way, but you can't. Okay, so if we're going to add 3 fractions together, what do they all have to have? Common denominator, the funnest thing in the world when it comes to math, especially when there's letters and pieces and all that stuff. Now, look at the most complicated denominator. Which one's the most complicated? Yeah, the x minus 2 squared. We need all of them to look something like that, right? What does this even mean? What does x minus 2 squared mean? Yeah, it means there's 2 x minus 2's there, right? How many are here? 1. How many does it need? 2. It needs 2. It needs another one, doesn't it? So the second fraction gets multiplied by another x minus 2. But if the bottom part gets an x minus 2, so does the top. Okay? So that's going to fix the middle one. The last one, how many x minus 2's does it have? None. So it needs 2 of them, right? So I'm going to multiply that bottom and top by x minus 2 squared. Now I got a little bit of multiplying to do. So we will not do that with 9x2. No, it doesn't need anything because it's already got 2 of them. Right? So we don't have to do anything to it because it's got x minus 2 twice. This right here is that. That's the same thing. Just like 1 times that is the same thing that this one has.
We still put the square at the top.
Yes, the squares, because it had to have 2 on the bottom, it has to have 2 of them up top. Now we're gonna have to multiply this out on top.
At the top of the 15x, I don't have to have two.
No, it'll get there when we multiply all this out.
Never
It's
mind.
yeah, it doesn't need to because we only put one there. This one we put two of them there. Okay. All right, now let's multiply out the numerators. Oops, too far. All right. So we have 9x squared, negative 15 times x, be negative 15x squared, plus 30x. So all I did was distribute the negative 15x to both of those. Now, I'm going to do a little scratch work over here with the x minus 2 squared. X minus 2 times x minus 2. Yeah, x squared, x times x squared, negative 2x. There's another negative 2x. There's plus 4. So that's x squared minus 4x plus 4. But I'm still multiplying that by 7 because that's what's in the numerator of the blue fraction. So 7 times x squared, 7x squared. 7 times negative 4 is negative 28x plus 28. All of that now is over x minus 2 squared. Yeah. We were just multiplying out the numerators. The denominator we made the same. We made them both be, all three of them be x minus 2 squared.
So we're gonna divide all of that into the numerator like the denominator.
No. We're going to simplify the numerators. So like terms. 9x squared, negative 15x squared, and 7x squared. Well, 9 plus 7 is 16. Yeah, it's going to be 1x squared. So those are all done. Now I got 30x and negative 28x. 2x plus 2x. And then, yeah, 28 is just there. And then we're going to leave x minus 2 squared in the bottom. There is our composition of h and k, or h composed with k of x. Fun stuff. And we found the domain already. We knew the domain could not be 2. Look at the denominator of a composite function. It's obvious that x can't be 2 because it would give us 0 down there. Even though it's squared, it doesn't matter. Okay. All right. Next section. 6.2. 1-to-1 functions and inverses. All right, 1-to-1 functions. One-to-one functions have to be a function first. What's the rule for being a function?
Vertical lines have two y values. Yeah, for one x.
All right, so vertical line test on a graph would decide if it only touches it once, then we're not repeating what values?
X value.
X values. For to be a function, it's a vertical line test or no repeated x values. That's just to be a function. To be a one-to-one function means you only map one x to one y. So you don't repeat x's and you don't repeat y's, which gives us a horizontal line test when we go to the graph. So one-to-one functions map 1x to 1y. No repeating x's or y's. Okay, no repeating x's or y's. Okay, can't have either of those. All right. Now, determining if something is a one-to-one function, something we've got to be able to do, is the relation 1 a set of ordered pairs here. 2, -3, 6, -8, 11, 5, 15, 1. Is that a function first? Yeah, no repeated x values, 2, 6, 11, 15. None of the x values are the same. Is it a one-to-one function? 1, 5, -8, -3. No repeated y values. So yes, it is one-to-one. Yes. Just a yes, no kind of thing there. We had a set of ordered pairs. Say -13, +3, -5, 6, 8, 3, 16, 9. Is that a one-to-one function? No. Why? Y is repeated. Repeated y value. That throws it out of being one-to-one. Okay? If we're given a graph, so I'm just going to sketch a graph. Here's a coordinate plane. That's your y-axis. That's your x-axis. Something like that. There's just a graph. Comes with some polynomial function. Okay? Does that pass the vertical line test?
Yes.
Yeah, easily. Now, to be a one-to-one function, you have to pass a vertical line test and a horizontal line test. Does it pass the horizontal line test?
No.
No, because if I put a horizontal line anywhere in this general area, it's going to touch that graph twice, which fails the horizontal line test. So this is not one-to-one. And it fails the horizontal line test. All right. Three parentheses x minus 4 squared plus 8. Is that a one-to-one function? How can we know so? Let's think about what kind of function it is. It's quadratic. What do we know quadratics do? A parabola, right? So it's this kind of shape, right? Could that kind of shape pass the vertical or the horizontal line test?
Yeah, it's not touched.
Horizontal line test, it's going to fail it, right?
It's gonna fail it.
Yeah, because it's quadratic, it's going to fail the horizontal line test. Would every even function fail the horizontal line test? Yeah. Because if it's x to the 4th power, that's like a quadratic, right? It may have a bunch of little squiggles in the middle, but it still does the same thing. It failed the horizontal line test somewhere. Does every odd function pass the horizontal line test? No. Example would be something, if you had some sort of cubic function that did this, that would be a failing. That's an odd function, but it fails the horizontal line test. So not every odd one is one-to-one, but every even one is not one-to-one. It's something that you can.
So, but a cubic could pass the horizontal line test?
Yeah. Here's an example. F of x equals x cubed. That passes. If you graph that, it'll pass. Because it does the hump in the middle, the graph of that one is that green drawing there. Okay. That's what so it would pass because this part is not tall enough to intersect twice. So there are some odd ones that do pass. I get technically there's an infinite number of them, but it's a smaller infinite number of them than there are that fail. It can't touch it twice. If it touches it twice, it fails. It's okay. Yes. Try. All right. Well, what good is a one-to-one function? A one-to-one function have inverse functions. That doesn't necessarily mean that functions that aren't one-to-one don't have inverses, but it means that their inverses aren't functions. So one-to-one functions have inverse functions, and functions that have inverses are important.
So like, is there like a name for relationships that aren't functions?
Non-functions.
Is that like they could either not be there's like nothing else, either it's a function or it's not, like nothing you can really do with non-functions.
Well, you can do a ton of stuff with non-functions, but as far as an application in algebra, no, not much.
Okay.
Yeah. Yeah, there are a lot of things that aren't functions that have some application to them. All right. One-to-one functions have inverse functions. Inverse functions interchange the domain and range. Interchange the domain and range. The good old country boy way of saying that is they swap X and Y. Okay? They do some swapping. We traded out X's and Y's. That's what an inverse does. Okay? All right? So, with that being said, let's look at a function. I don't know what letter we're on here. E. And here's a function. A little weird looking for us to write it as f of x, but it works that way. So there's just a function. It's a set of ordered pairs. We know it's a function because the x's don't repeat. Is it a one-to-one function? Yeah, because the y's don't repeat either. Okay? The inverse of that interchanges the domain and range. The domain is the what values? X values. The range is the y values. So again, we're going to swap x and y. Right? So if I swap x and y on this first order pair, yeah, 6 becomes the x, -3 becomes the y. We just turn that ordered pair around. So 6, -3. The next ordered pair would be 7, -1. And that carries on. 13, 2. -8, 5. The notation that you use, f with like a -1 in exponent, but you read it f inverse of x. But it's written like a -1 exponent on that f. F inverse of x is what that is written as. And that's the inverse of that function. Now, are they going to give you a bunch of easy ones like that? No. But that's the general idea, okay? Now, let's look at some that are a little less elementary and a little more. So here's our function. F of x is equal to 6x minus 7. Just a good old linear equation. Slope of 6, y-intercept -7. We know that that's an odd function. It's a straight line. Goes up and to the right with the slope of 6. It passes the vertical line test. It also passes the horizontal line test. We know it's a one-to-one function. Let's find the inverse of that function. So to invert that, what do inverses do? Swap x and y. So I'm going to swap x and y in my problem. Okay, remember f of x is the same thing as y. right? So I just rewrote the problem with y there instead of x. Same thing. Swap x and y, because that's what inverses do. And now to get the inverse, I solve that for y again. So I solve the red one for y. So add 7. X plus 7 equals 6y. And then divide by 6. I'm going to divide each one of them individually by 6. 1/6 x plus 7 over 6. The inverse notation, official answer, 1/6 x plus 7 over 6. Technically, if you did this, it's right. But anytime it's linear, I tend to write it like a linear.
So like a linear equation is inverse is always also a linear equation, right?
Yes. Yeah, linear is a little bit.
But not quadratic?
No.
Huh.
Not always. Because quadratics, remember quadratics not 1-to-1.
Oh,
So
yeah.
we gotta have something special happening with that. We'll get there. Give it time. All right, here we go. Here's a function, f of x, 2x plus 1 over x minus 1. And they tell us x can't be 1. Why'd they tell us that? Yeah, that would make it mess up. Okay, so they're just telling us the restriction on the domain like we didn't know. We're smart, we knew that. All right, now, that's a 1-to-1 function. I'll go ahead and tell you that. It has an inverse. Let's find the inverse function for that. Okay, so what's the inverse do? Swaps x and y. So everywhere there's an x, there's now a y. Oh, on it, they put 2 of them in there. My dad would say, Lance, who Lance was, but he got to blame for a lot of things when I was a kid. All right, so how do we get the y minus 1 out of the denominator? Yeah, if I multiply by y minus 1 on both sides, it'll get rid of that one in the denominator. But now I got y's on both sides. And I can distribute here and get xy minus x equals 2y plus 1. Now, what am I trying to get by itself again? Y. I'm working to get y by itself again. What has y's? This guy has y, and then the 2y. They both got y's. This does not have a y. This does not have a y. So my job is to get everything that's got a y together. Right? So, and get everything that doesn't have a y at all to the other side. Okay, so I'm gonna move this x over here, and I'm gonna move this 2y over here, right? It makes sense to do that. Get the x's and the things that don't have y's and the things that do have y's together. So I'm gonna subtract 2y, and I'm gonna add x. That cancels. This cancels, and I've got xy minus 2y equals x plus 1. So it's closer. And here's where you got to think a little bit of algebra. Maybe algebra 1 skills. What's the GCF of these two? Y, greatest common factor. The thing that both of them have. Both of them have a y. So I can factor that y off of and pull it out to the front, like reverse distributive property. It's like both of them had a y, I'm going to pull it back out and get y parentheses x minus 2. Okay. Well, that looks better. It still ain't done. Nope. If I distribute it, I can get back to the purple step. That doesn't do me any good. Why can I divide by x minus 2? What's going on between y and the x minus 2? Yeah, it's y times this parentheses stuff, so the opposite of times in it would be dividing. So dividing by that x minus 2 So f inverse of x equals x plus 1 over x minus 2. What can x not be? 2. Because we're smart and we know that.
So the restriction earlier doesn't carry over to.
The restriction earlier was on the domain of the original function, and this 2 is actually the y value that went with that x value is really what that is. So this is the domain of the inverse is the range of the original. And the range of the inverse is the domain of the original. That'll get you confused pretty quick if you start thinking too much about that. Don't think too much about that. Get the thing solved. That's what my goal is for you here. All right. So we're going to get into that idea with the quadratics. This is next example. Okay. If we're dealing with the quadratic, g of x is x squared. And then they're going to have to put a restriction on that. X is greater than or equal to 0. Okay. That restriction, what letter we're on here? H. That restriction makes this quadratic 1-to-1. Because if I graph x squared, just plain old x squared, real easy one, normally that's what it looks like, right? But if I'm doing only the x's that are greater than or equal to 0, what part of that graph do I have? Yeah, the right-hand side of it. So right now, what I've got drawn doesn't pass the horizontal line test. But if I only graph the part that's greater than or equal to 0 on the x's, that does pass the horizontal line test. No. Okay. This is just a restriction on the domain. Okay. So that it will be 1-to-1 so that we can find the inverse function for it. Okay. So to find the inverse of that, what do inverses do? Yeah, swap your x and y. So x equals y squared. Now, how do I get y by itself? Take the square root. Square rooting. Square rooting is not a verb. So you take a square root. All right. Now, notice I put plus or minus in front of that because anytime I introduce a square root into a function, I don't know whether I'm using the positive sign or the negative sign. Because the square root of 25 could be 5. The square root of 25 also is negative 5. So I have to have that plus or minus here. Okay? So the square root of y squared is going to be y. And then it's plus or minus the square root of x on that side. Which one do I use? The plus or the minus? Why?
Because the original problem was positive.
What part of it was positive?
The restriction on the domain.
The domain told me to use the positive x values, and the graph, the positive x values gave me what kind of y values? Positive ones. So that's why we're using that. Okay? That not necessarily because this said x's are greater than or equal to 0, because the graph of that, the y values that I got were positive. Okay? So the domain of this is only the x's that are positive. So g inverse of x equals the positive square root of x, and x is greater than or equal to 0. There's our inverse out of that. Okay. So finding inverses, not an incredibly difficult thing. And inverse, the idea with the inverses and inverse functions is that once we build up this idea of inverses, we get to much more complex functions. If we can get the inverse function, that can be used to solve an equation using an inverse function. So we'll get to that later in chapter 6. Let's get to verifying. Still same section. Verifying function inverses algebraically. Anything that says algebraically is beautiful because it's mathematics and it works. But also means this work to do. Okay, if f of x and g of x are inverses or inverse functions, then f composed with g of x equals x and g composed with f of x equals x. Composition is the tool for algebraic verification of inverses. Okay. Here's our functions. F of x is 2x plus 3. G of x is 1/2 x minus 3. And x minus 3 in parentheses there. We want to check to see if these two are inverses of one another. Algebraic verification of that. Okay. F composed with g takes g of x, plugs it into f of x. 2 parentheses 1/2 x minus 3 plus 3. If I multiply 2 times 1/2, what's half of 2? 1. So that makes that easy. So that makes that x minus 3 plus 3. What happens to the 3's? They cancel. It verified in that direction. So f composed with g is x. It's verified in the other direction. G composed with f. So we're taking f of x and putting it into g of x. 1/2 parentheses 2x plus 3 minus 3. Order of operations says do the inside of the parentheses first. So that's going to be 1/2 times 2x because the 3's cancel each other. It's half of 2x. 1x. It verified in that direction. Okay. If you get anything besides plain, nothing fancy, plain old x, you get anything besides that, they're not inverses. Okay. If it's negative x, not inverses. If it's x plus 2, not inverses. If it's the square root of x, it's not an inverse. It has to be plain x to be inverses with the composition, algebraic verification. Okay. There is a graphical verification. I'll show you that real quick. Graphical verification is a reflection across y equals x. Okay. So I'm going to graph these two on my graphing calculator. Okay. So y1 is 2x plus 3, y2 is 1/2, and then x minus 3. The third equation there is the y equals x line. That's the one they're supposed to reflect across. If they're inverses, they'll reflect across that. We know these two are already inverses because we checked it algebraically. So we should see that reflection. I graph that. The blue one, that's the 2x plus 3. The red one is the 1/2 parentheses x minus 3. The black one is the y equals x line. Does it make sense that if I folded this blue one over across that line, it would meet up with the red one there? Same thing down here. They meet up. Look where they cross. Right on the y equals x line. That's a good clue. Graphical verification is sometimes hard to see if you end up with like rational functions. They're harder to see because you got pieces here and here, and you're like, oh, if I fold this, does it match up perfectly? It may not. It's harder to see. Algebraic verification is much better because it's absolute. Either you're getting X or you're not. Graphical verification is just a good quick check. That if it looks like it is, maybe I know, okay, I should be getting the right thing here. Maybe I'm making a mistake in a sign or something somewhere. Okay, so graphical verification is good for a quick check, but algebraic verification is definitely the best method for verifying. Okay. All right. Next section. We're moving on. 6.3. Exponential functions. F of x equals c a to the x. Okay. C, that's your initial. If your name's like Calvin or Connor or something like that, your initial is C. No, your initial is your initial amount or value. It's what we start at. It's what we got at 0. A, that's our growth or decay factor. X is the same old X we've been dealing with. X in exponential functions, that X may be days, maybe hours, maybe minutes, could be years, who knows, depending on the context of the problem. But the initial value, that's the amount you have at 0, whatever X is. When X is 0, that's your initial amount. Because anything to the 0 power is 1, so 1 times C is C. The growth or decay factor, depending on what A is, whether it's growth. If A is a bigger number, we're going to be growing. If A is a small fraction, we're going to be decaying. Right? Because if you multiply something by a half, you get smaller, right? And then exponential means you multiply by a half again, and it gets smaller again and again and again. So exponential growth, A is a bigger number. Decay, A is a small number, like less than 1. Okay, that's the differences. All right. Is a set exponential. That's what we're playing here. Order pairs 0, 5, 1, 10, 2, 20, 3, 40, 4, 80. All right, so determining if that's exponential. One method would be to graph those ordered pairs and see if they made a curve that either did this or this. Well, we only have 5 of them, so it's going to be hard to determine if that's that kind of curve. But we can look at the individual Y values and decide, hey, are they growing at the same or at different rates, or their ratios different? Okay, so the ratio of Y values is what we're going to use to test this. 10 over 5. How much is 10 over 5? 2. What's 20 over 10? 40 over 20. 80 over 40. It's a constant rate, right? That rate is your growth factor. If the ratio of your Y values is the same, or really, 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 really close, then it's exponential. The ratio. In linear stuff, you had to have the difference in Y over the difference in X had to be the same, constant. That made it linear. Quadratic, you had to have that quadratic shape happening, that if X was 2, then you got 4. And if X was -2, you also got 4. You had that symmetric thing going on there. With exponential, the ratio of the Y values, if it's the same or really, really, really close, then that is exponential, and that ratio is your growth factor. Okay? So if we're going to write, yes, it is exponential, we're smart enough to actually write the function. If I know the growth factor, the ratio of the Y values, the same thing. It's 2. Where's that go in my function? Up here. Where A is. So I know I have 2 to the X. What's C? It's what's happening when x is 0. What's happening when x is 0? 5. So we actually wrote the function for that. Not only did we find out it was exponential, we wrote the function based on that. Okay. Is this growth or decay? Growth. Not because I just wrote growth factor, but because the A value is what? It's a big number, right? And the Y values, as X increases, what are the Y values doing? Increasing more and more every time, right? Okay. So let's look at example B. Another set. -1, 32, 0, 16, 1, 8, 2, 4, 3, 2. Well, there obviously looks to be some sort of pattern there. 32, 16, 8, 4, 2, all being, some sort of power of 2. So there's a pattern going on, but is that pattern exponential? How do I decide? It's the ratio of the Y values. 16 over 32. It's a half. 8 over 16. It's also a half. 4 over 8. Also a half. 4. So a half. Is this growth or decay? Decay. Obviously, the Y values are getting smaller and smaller as we go. So this is decay. So, yes, f of x. What's C? 16. The 1/2 is our growth factor or decay factor in this case, since it's going down. It's a small number, and it's to the x power. Fairly simple ones that you can find the function of fairly easily. Okay. Deciding if it's exponential. Ratio of the Y values. Quick way to decide that. A little bit better sometimes than graphing, because graphing, if you only got 3 or 4 points, you may not get much of the curve. So it's hard to tell. But the ratio of the Y values will always tell you that on there. Exponential. All right, let's look at this one. F of x equals 2 to the x. So that's exponential, right? If I put +4 on the outside there, how did that, think about back to chapter 3. How did that do our transformations? Moved it up 4. A +4 on the outside shifts it up 4 units. Vertical shift 4 units up. If I had this function, f of x equals 2 to the x minus 3. If the -3 were out here like this +4 is, like down here, yeah, it would be down 3, but it's not. It's up there with the x. To the right 3. Good job. Two to the -x minus 5. I agree that it's reflection across what? Yes. Reflection across the y-axis. A negative on the x changes it across the y-axis. So it's changing the sign of the x value, so that moves it across the y. The negative were down in the front, that would be across the x-axis. Like if the negative were down here, that would be across the x. So remind yourself of those transformation rules. Very easy problems to get correct, knowing, hey, it's just shifting that thing up and down, left, right, that sort of idea. Really, really simple ideas. Okay. Now let's get into solving some equations. And this is where it gets a little bit easier maybe. 2 to the x plus 5 equals 2 to the 8th. What do we notice about both sides of this problem? They both have the same base, and both have exponents, right? If the bases are the same, and they've got exponents up here, what do we know about those exponents? They would have to be what? They'd have to be the same, wouldn't they? If 2 to something is equal to 2 to the 8th, then this something over here has got to be 8, right? So x plus 5 equals 8. So x would equal what? 3, yeah. Subtract 5, x equals 3. Because the bases are the same, we're allowed to do that. Okay? So right there beside of it, 2 to the x plus 1 equals 16. Okay, oh. But you just said if the bases were the same, we could set the equations up. This guy's a real jerk. Changes the rules every time we figure it out. But what about 16? It's a power of 2. It's 2 to the what? It's 8 times 2, but that doesn't help us. 2 to the third would be 2 times 2 times 2, which is 8. 2 to the 4th. Oh. So there, now the bases are the same. My equation is x plus 1 equals 4. Subtract 1. And x equals 3. So x is 3 all the time. That's the only answer we get. Good enough. Just kidding. X is not 3 all the time for folks watching the video that didn't come to class today.
Is there like a formulaic way to figure out like if something's like an exponent? Like, okay, so we need to find out that 16 was something to the 2 power of something.
This is how I would do it. Remember doing factor trees back in elementary school?
Oh yeah.
It's been a while, but it's not something you use every day, right? I can break down 16. I know it's 8 times 2, and then I know 8's composite, right? So it'll break down some more. It's 4 and 2. There's 2 and 2. So then I look at the prime pieces. That's 2 to the 4th power out of that. Same way with 81 here. What do we know about 81? It's divisible by 9. It's 9 times 9. 3, 3, 3, 3. Oh, it's 3 to the 4th power. So 3 to the 5x equals 3 to the 4th. My equation then becomes 5x equals 4. X is 4/5. It's not. Oh, yeah, we had this awesome thing going. All right. All right. Here's a funner one. Yeah, funner.
My wife teaches math, but she's an English nerd too, so she really wants me.
All right. So 4 to the 2x minus 1 and 8 to the x. Can I write 8 as 4 to a power? I could, but it'd be this really funky decimal thing, which tells me, no, that's not how it's supposed to do, because it shouldn't be that hard, right? Well, what's the relationship with 4 and 8 that might be handy?
You can multiply 4 by 2.
Yeah, 4 times 2 gives me 8, but what's 4? It's 2 times 2, right? It's 2 squared. So that would mean 8 is 2 to the what? 2 to the 3rd. Oh, so I actually have 2 squared to the 2x minus 1 equals 2 to the 3rd to the x. But that's not that bad. You got the bases the same. So what's the rule for the exponents, though, right here? You multiply them. So this is 2 times 2x minus 1 And then the other side is 3 times x. I'll do this side. What's the other side? Oh, now we got a nice easy equation where the bases are the same on both sides. The exponents become the equation. 2 times 2x is 4x. 2 times 1 is 2. Now we have 4x minus 2 equals 3 times x is 3x. Solve it.
X equals 2.
Okay, by subtracting 4x, negative 2 equals negative 1x divided by negative 1. X does equal 2, not 3. Okay, easy enough. Let's make it more fun. I'll scroll up. That good? All right. This is a little tougher because it's got a fraction in it. Because everybody loves fraction.
So do we want to express 9 as a fraction too? No.
Actually, we want to express 1/27 as not a fraction.
We just did that.
Did we?
Yeah.
The math guy.
Yeah.
Jay. Okay, so we want to re-express these as the same base. So what's the relationship between 9 and maybe not 1/27, but maybe just 27? Their powers are 3. 9 is 3 what? 3 squared. Okay. So if 9 is 3 squared, that means I could rewrite this as 3 squared to the 2x. Now, 27 is 3 to the third, right? But again, I want to write that as not a fraction. So how do I make this not a fraction? Yeah, it's 3 to the negative 3 equals 3 to the 4x, right? Because 2x times 2, that's where the 4x is coming from. And then now we got an easy equation to do. Divided by 4. X is negative 3/4. Okay, that's fun. 4 to the 3x squared equals 8 to the x. There's an exponent on an exponent. That's it. No more minutes. Okay, now, we already have dealt with 4 and 8. Right? So we're going to think about bases for that. What are the bases for those?
2 to the second.
All right, 2 squared to the third. So this 2 squared to the 3x squared, 2 cubed to the x. So that ends up being 2 to the 6x squared equals 2 to the 3x. Okay, well, that's wonderful. Now the bases are the same. What's my equation? Okay. Now that's what kind of equation?
Quadratic.
It's quadratic. So what do we have to get it equal to solve it?
0.
0. So I'm going to move the 3x by subtracting it. So that's going to give us equals 0. And then I've got all of the quadratic options that I learned back in chapter 4 or algebra 1 or algebra 2 or some other math class. Okay. I'm going to use factoring because the greatest common factor between those two is 3x, leaves 2x minus 1 equals 0. What do I do with each of those factors? Set them equal to 0. 3x equals 0. 2x minus 1 equals 0. Solve each of those independently. X equals 0 plus 1. Divide by 2. X is a half. Okay. 2 answers on that one. Makes sense that we had an x squared in the exponent, so you get a degree of 2, so you'd have 2 answers, right? Out of that. So nothing really different about that other than you've got a type of equation at the end that you've got to work with that you've worked with before. Okay. All right, let's do this one. E to the 2x equals e to the x minus 5. E is a number, guys. It's called the exponential number. E to the first power is about 2.71, and then some change after that. It's a number that occurs enough naturally in biology and bacterial growth and things. It's kind of like pi. It showed up enough that they said, okay, we got to give it its own little thing. Pi was already taken, so they gave it E. Why they didn't give it F, I don't know. Maybe they didn't want it to have issues, so they gave it X. They gave it E. Are the bases the same?
Yeah.
So is this any different than what we've been doing? No. Okay. So solve it. 2x equals x minus 5. Subtract x. X equals negative 5. You're done. Now that's too easy, right? Let's make it not so easy. Okay. So here I've got 2 things on the left side have base of an E, and they're multiplied together. What are the rules for exponents when the bases are the same and we're multiplying? Add them. That's right. So this is really e to the x squared plus 7x, which is now a problem very similar to L, and the bases are the same. So my equation is now these things. X squared plus 7x is equal to negative 12. Got to move the 12, right? Just by adding 12. That's what I'm doing there to get there. And then solve it. Either a quadratic formula or factoring. Yeah, factoring works pretty easy on this one. There's a 1 in front of x squared, so I don't have to group. If there's a 1 in front of x squared, I can go straight to my factors. If there's anything else in front of x squared, I've got to do grouping. Negative 3, x equals negative 4. That is the quadratic formula, which would get you the exact same 2 answers for this. A little longer way of getting there, but it'd get you the same 2 answers. Okay? All right. I don't know that I'm going to get through this section. Yeah, maybe. 6-4. The projector problems at the beginning are coming back to haunt me. Logarithmic functions. Logarithms. Logarithms. A logarithm right? is an exponent. That's what you got to remember. A logarithm is an exponent. Okay? So if we're going to rewrite these logarithmic functions or equations as exponentials, I'll show you how to do that. Log base 3 of x is what is y is equal to. Okay? A logarithm is an exponent. What that says is that a logarithm, this thing, is equal to an exponent. Okay? This right here, the y is an exponent. What's the base of the log? It's 3. So the base of the exponential is 3. Okay? So 3 to the y is equal to x. Whatever the base of the log is, equal is your exponent. What's in here? That's what it's equal to. Log base 2 of x equals 3. What's the base of the exponential? 2. What's the exponent? 3. Because the logarithm is equal to the exponent. And then we could solve that equation if we need to. We're not worried about that right now. What's the base? 5. What's the exponent? What's it equal to? What's the log equal to? X. Whatever it's equal to is the exponent. Okay? We're not working anything here. We're just rewriting is all we're doing. We'll get to the working part of it probably next week. Natural log of x equals y. Here's the kicker on the natural log. Natural log is log base e. Okay? So the base is e. What's the exponent? Y. So natural log is log base e by definition.
What is this, like the rate itself? Or something?
It's related to that. We're dealing with logarithmic functions here that are not necessarily dealing with only biological applications, but they tend to be a big part of this. Log x equals 3. Anytime that log is plain like that, it's a base 10. It's the understood base 10. When log doesn't have anything written there, it's an understood base 10. Okay. So this would be 10 to the third equals x. The reason it's the understood base 10 is that's the kind of number system we live in, is a base 10 number system. Because we have a ones digit, a tens digit, a 10 squared digit, which is hundreds, 10 to the thirds, of thousands. We have that a base 10 number system that we live in out of that. Let's go the other direction real quick, and I guess we'll have to cut it off here. Yeah, I'm gonna get to all that mess. All right, let's go the other direction. 3 to the x equals 27. We're going to rewrite this as a log. What's the base on the x with this exponential? 3 is the base. So we're going to use log base 3. Remember, when it's a log, what the log is equal to is the what? Exponent, what's the exponent on this one? X. So where does that leave the 27? Right there, yeah. What's the base there? 10. So that turns into log of what is equal to what? Log of y is equal to, remember the exponent is always what it's equal to. There, get h. A to the fourth equals 24. Log base A. Yeah. So even when the log is not a real, the base is not even a number, we could rewrite it as a log. Okay. Being able to do that is a fairly simple idea. Okay. We'll stop there for the week, and we'll finish up this section on Monday of next week, and kind of continue our ascent into college algebra. Yeah.